Good evening, everybody. Thanks for coming. We're so excited to have everybody here tonight. I'd like to also note that today is our first Discovery Lecture Series back in person since COVID. It's been a long run, but we're super happy to be back in person. And this is also our very first hybrid Discovery Lecture. So we have a handful of people here in the audience, and we have a handful of people, you at home. So welcome, everybody. Thanks for coming. I am Dr. Julianne Passarelli. I'm the Education and Collections Curator here at Cabrillo Marine Aquarium. I'm going to just start with some information for our online viewers. So those of you in the audience, just bear with me. This is a webinar style platform. So you cannot see yourself, nor mute yourself, or unmute yourself. But any questions you have, please put them in the Q&A feature at the bottom of your screen. Perhaps it's at the top, but please put it in the Q&A feature. We will get to questions at the end of the lecture. During the lecture, if you think of a question, go ahead and put it in the Q&A section. We will also be monitoring the chat. Cabrillo Marine Aquarium is owned and operated by the City of Los Angeles, Department of Recreation and Parks, and we are extremely grateful for the city's support. I would also like to thank the Aquarium Director, Kristin McCarran, and the Programs Director, Jim DePompe, for their support, and a huge thank you to everyone who's joined us tonight. The aquarium is open now Tuesday through Sunday from noon to 5. So we had been closed on Tuesdays since we had opened last year, and now we're open on Tuesdays again, and our hours remain from noon to 5. All capacity restrictions have been removed, and we have resumed all programming, and we're following all city health department requirements. In addition, proof of vaccination is required. So if you're attending anything at the aquarium, please be prepared to show proof of COVID vaccinations, and masks are also required at all times. We have some upcoming programs I would love to tell you guys about. We do monthly beach cleanups, the first Saturday of every month, and the next one is tomorrow on June 4th at 9 a.m. We will also have one in July, but it won't be the first Saturday because it's Trashmageddon, and it'll be the Tuesday right after the 4th of July. So that'll be on July 5th at 9 a.m. And if you want to help us clean up the beach after 4th of July celebrations, join us for Trashmageddon on July 5th at 9. And then we also have a Walk Cabrillo on Saturday, June 11th at 11 a.m. Pack a snack and join a walk of the Cabrillo Coastal Park guided by CMA education staff. And our last Meet the Grunion for this season is on Thursday, June 16th. Doors open at 9 p.m. Join us to see the amazing California grunion spawn on the beach. It's the last one of the season, and the runs have been really good this year on our beach. We just had one on Wednesday, and it was amazing. I am pleased to announce the remaining 2022 Discovery Lectures will be on site and will continue to do hybrid. We apologize for the technical difficulties, but we figured it out, it seems like. And the upcoming lecture is on August 5th. And it's Dr. Shauna Goffretti from Occidental College, and she's going to be talking about marine vampires, blood-feeding invertebrates, and their bacterial accomplices. So you can RSVP like you did tonight and receive the parking code if you would like to attend in person, or you can receive the Zoom link if you would like to watch it from home. And we do have the other two lectures scheduled for the rest of 2022. October 7th is Dr. Jennifer Burniford from Cal State Fullerton, and December 2nd is Dr. Doug Fudge from Chapman College. If you have missed any of our past lectures, don't worry. We have recorded and archived all of them on our website on the Discovery Lecture Series page. Just scroll down to Lecture Archives 2014 to 2022, or you can go directly to the CMA YouTube page. And again, if you're interested in the August lecture, just be sure to RSVP to get that info. Okay. It is my pleasure and honor to introduce tonight's speaker, Dr. Austin Hendy from the Natural History Museum of Los Angeles County. Dr. Hendy is the curator of invertebrate paleontology and is a paleontologist, geologist, adventurer, teacher, and proud San Pedro local. He completed his early studies in New Zealand before moving to the United States to complete his doctorate at the University of Cincinnati. Austin held postdoctoral fellowships at Yale University, the Smithsonian Tropical Research Institute, and the University of Florida before joining the staff of the Natural History Museum in 2014. As curator of the Invertebrate Paleontology Collection, he oversees the second largest collection of fossil invertebrates in North America, supervises collection staff and vibrant student interns, teacher training, and volunteer initiatives. Dr. Hendy conducts fieldwork through Central and Northern South America and Western North America. The title of tonight's talk is Palos Verdes Underwater, a paradise 150 million years in the making. Thank you, and we welcome Dr. Austin Hendy.
Well, thank you, Julie, for that very kind introduction. And I have to say, Julie is under pressure. She is solid tonight. We had a few technical difficulties before everyone arrived, and I was very impressed. We got through it all. All right. That's right, I got to press this button. And hopefully something will happen.
Is it not moving?
It's not working. I can probably go that way. There we go. I've woken it up. Excellent. Well, you heard a little bit about me already, but I always start off my presentations by telling you where I came from and what I do as a curator at the Natural History Museum. One of my responsibilities is to look after your natural heritage. So it's the Natural History Museum of Los Angeles County. We have tremendous collections in our museum from all around Southern California, particularly in Los Angeles County and the city of Los Angeles. And so it's my responsibility to conserve those collections, help them grow, and study them. And it's also a privilege of mine to work with tremendous staff who look after those collections, educators, and exhibit makers. And a lot of the work that we do at the Natural History Museum is built around this theme of, for, and with Los Angeles. And that's perfect because I just love to share what I have in my collections, what I know, the knowledge, and really give back to the community. So it's a great honor to be talking to you tonight. I've been looking forward to this for many years now. COVID kind of got in the way of that. So here we are tonight. So thank you for coming.
I'll move the mic up a little bit. This mic.
Okay.
Yeah, there we go.
All right. Excellent. Well, like many geologists and paleontologists, probably many kids, when I was a little sprout, I was digging around in the dirt, fascinated by rocks. I think this is me when I was about 5 years old, while touring France, while my parents were looking at chateaus. I was busy inspecting the building blocks and masonries used in these historic buildings. And then, as I got a little bit older, in order to get me out of the house, I was very fortunate that my father was a geochemist, did a lot of field work with his students. And so to get me out of the house, I would go on field trips with my father. So you see me marching around here with a hard hat. Maybe this is about age 6 or 7, directing graduate students on where they should be collecting their samples. All right, and fast forward another 20 years or so, and I'm a fully fledged field geologist. I love being out in the field. I love working in tropical, sunny beach type environments. I actually study both the modern marine environment and the fossil record. So really this is a perfect setting for a paleontologist like myself. But I've had many exciting adventures, particularly in Central and South America. Wonderful places to work. But nowadays, I'm at the Natural History Museum and looking after this tremendous collection of your local natural heritage. Also the proud father of two kids that are in local LAUSD schools. I try and rope them into my research when possible. That seems to have been waning of late, but during the pandemic, it was great to have some extra hands to help. And of course, knowing teachers in the school system has really encouraged me to offer my expertise. And so I provide a lot of professional development to teachers in the school system. So this is a program that we ran last year at the Natural History Museum. And then you'll often find me out on the weekends leading field trips. So I've been running a series around the Palos Verdes Peninsula this year. And this was from about a month ago down in Cribillo Beach, talking about the geology and paleontology of that area. All right. What inspired my presentation today is an exhibit that we've been working on at the Natural History Museum. This really was my COVID passion project. Got a phone call in the first week of our lockdown, inquiring whether I had any ideas for an exhibit, and really jumped on that and spent the next 2 years having Zoom meetings, lots and lots of Zoom meetings, and bringing this exhibit to life. And I'm very proud to say it opened about 6 weeks ago. I spent the last 3 days in that exhibit gallery with little kids. So if you're a teacher out there, oh my goodness, hats off to you. You guys are amazing. I don't know how you do it, but I can tell you that the kids are loving this exhibit. So if you have a chance to get down to the museum, please go check it out. What we try and do in this exhibit is really shine the spotlight on discoveries and the discoverers, the stories behind the fossils that were found around the city of Los Angeles. Obviously, the Natural History Museum employs a staff of paleontologists, but many of the discoveries that we've made, many of the iconic specimens that we have in our collection have been found by everyday Angelenos. So we have Adam, Aaron, and Avery on the left there, young kids who have been digging up holes in their backyard. I'm sure many of you are familiar with that, but actually finding fossil discoveries in their own backyard or their own local parks. We have Dominic, who's a school teacher, posing with his fossil fish that he found. And then we can also go back in time, and there's this gentleman, Mr. F.W. Maley. I haven't figured out his first name yet, but I'm going with Frank. It seems like an appropriate first name. Frank was a plumber and was digging a ditch in East Los Angeles in an avocado field, 80 years ago. And so I love telling stories about these collections. There's so many fascinating aspects to them, but just thinking that 80 years ago we had avocado farms, just a mile or so away from downtown Los Angeles, I find quite fascinating. Anyway, Frank he hits a bone while he's digging this ditch, and it turns out he's a regular at the museum, so he knows what he's hit. And so he calls up the museum and says, hey, you guys, I've got a whale. And they came out and collected it. And so 1931, this is our first whale in our collections at the Natural History Museum. And I think we now have one of the largest collections in the world of fossil whales. They're very rich in the fossil record around Southern California, but it all starts with Mr. Maley. Okay, and discoveries continue to the present day. In a city like Los Angeles, there's lots of construction work going on, and often as a result of that construction work, paleontologists are hired to mitigate any loss of, again, your natural heritage. And so we have fossil discoveries being made every day by contracted paleontologists, and many of those will end up in the Natural History Museum. So it's those stories that we try to put on display in the exhibit. Secondly, I really wanted to connect the collections that we have with the communities around Los Angeles that they came from. The blue dots here on this map represent fossil localities around Ventura, LA, and Orange County, and you see they're all over the place. But they now all reside in our collections, either downtown or in a couple of the warehouses that we hold. And it's a shame that we can't share those stories with more people. So one of the goals of this exhibit was really to reconnect those collections with the communities that they came from, and as a result, educate Angelenos about the fossil record in their own city and what it tells us about past environments. All right. Okay, now, if you've visited Los Angeles as a tourist or you have a passing interest in paleontology, you've probably heard of the La Brea tar pits. And that may have been the only thing you've heard about paleontology in Los Angeles. It's a truly remarkable and unique location. It's a place where saber-toothed cats and mammoths are being excavated on a daily basis. I've got to remember how to advance the slides here. A tremendous fossil record being exhumed, prepared on site, and on display to the public. So these include extinct megafauna represented by bones or teeth. They may also include insects or fragments of plants or seeds, many of which tell stories about how environments have changed over tens of thousands of years. All right, but this is often where Angelenos' knowledge of the fossil record in this area begins and ends, and none of it involves being underwater. All right, but geology is everywhere around the city, and there's a spectacular opportunity to teach the public of Los Angeles about the geological history of this area, environmental change, and also our own human interactions with the environment, both on land and along our coastline. And I'm going to talk about a few of these landmarks during today's talk, so we'll just get all oriented here. We have the San Gabriel Mountains, the Santa Monica Mountains, and the Santa Ynez Mountains to the west, which collectively are called the Western Transverse Ranges, just a big mouthful there. Then Los Angeles Basin, or Los Angeles Plains, this flat area through the middle of this image. And then the Palos Verdes Peninsula, which borders the basin to the south. Okay, so these are landmarks that you can see almost anywhere throughout the city. If you have a look at a geological map of Los Angeles, you'll see a kaleidoscope of colors. And these really reveal a complex history of geological processes, some rapid, some gradual. And it's that history that we're going to discuss today in the context of the Palos Verdes Peninsula. All right. I often start these presentations by, and I'm often giving them to school groups, by asking folks to look around the city and see what they see. Strip away the buildings, the houses, the roads. What are some of the natural features that you see? And some of these features are landmarks, the mountains that we discussed earlier, the beaches. Maybe you see some remnants of the sand dunes by Redondo Beach. You got the foothills. You got the mountains in the background, the modern day coastline. These are all geological in origin. And what I like to do is by the time students finish presentations with me, empower them to go out and make these observations for themselves. And look around, see what they see, and try and figure out how it got there, right? So it's a fascinating story. How did we get to this understanding, and what role does the Palos Verdes Peninsula and San Pedro play in that discovery? So it starts in the 1850s. So there were some anecdotal comments on the geology of the area before that point. We had a lot of sailors sailing up and down the Pacific coast of Western North America, making observations of the cliffs or the bays and the mountains. But really no formal geology was conducted until the 1850s or the mid-1800s. And at that time, San Pedro was pretty much a quiet mudflat. The area that is now the port of Los Angeles was a quiet little town, extensive mudflats, and extending around the harbor. There'd be the occasional military ship coming into port or coming into the bay, but not too much going on. All right, so we had geologists like William Blake and John Trask, federal geologists. They were doing survey work, and they came out here and they visited very accessible sites, and usually, up and down the coast of California, usually close to settlements, close to ports, close to forts, for their own safety. They were military geologists, so they often went where the military sent them. They made cursory descriptions, and they collected a few fossils and rocks. Now, the paleontologists of the day did not go in the field, at least this far afield. So, the fossils and rocks that Blake and Trask collected would have got crated up and sent back to the East Coast, to the museums on the East Coast, in Philadelphia and New York. And it wasn't, FedEx same-day mail. It was going by ship, and they didn't always make it. And you can imagine how much context and vital information was lost along the way, even if they did make it. All those rocks and fossils are probably pretty jumbled up. All right. However, things were rapidly changing in California. The gold rushes of the late 1840s, and then the railways moving their way across the continent in the mid-1800s really required a lot of geological surveying, both to understand the landscape, but also the underlying geology. And with railways also came greater access by scientists. So those paleontologists on the East Coast could now come out here and visit. All right. Well, my animations are broken on this slide, but the state of California hired this man, and you see him in all his glory here. Although, let's get rid of, I'm not going to get rid of the horse. He was a gun-toting geologist. This guy's name is William Gabb, and he was hired by the state of California as their first geologist. They realized that mineral resources were critical, and so we had the gold rush. They were interested in finding more gold, more silver, other minerals. So they hired Gabb to go out and map the rocks. Unfortunately, he was a keen paleontologist, so he actually focused more on the fossils. And I understand that the state of California didn't really appreciate his biases, but he named a lot of the earliest fossils that we have known from California. All right. But back in the day, taking a gun with you in the field was essential field equipment to fight off those bears. Okay. The first comprehensive study of the fossils and the rocks of the Palos Verdes Peninsula was by a gentleman called Ralph Arnold in 1903. And he would have visited all of the extensive coastal outcrops between Point Fermin, probably up to the bridge, the Vincent Thomas Bridge. So there are extensive exposures along there. The town of San Pedro, as it was then, was starting to extend along the shoreline and cut back into the cliffs, and they're all fossiliferous. I believe this is a view looking from the 22nd Street Marina at the coastline at the time. Now, a lot of that land has been reclaimed, so it looks quite different today. But these are the hills that you see if you're enjoying a beverage at Brewery West or down at Crafted. Those hills up behind you, I think these are the hills in this particular image, and you see the mud flat in the foreground. So it's a setting that's changed considerably in that time. All right. So there we go. Here's a picture of some of the outcrops that he was looking at. And you see the lumber industry is very important at the moment. So there's a lot of lumber yards along that foreshore. All right, and there's Ralph Arnold. But I want to pay tribute to Martha Burton Woodhead Williamson, who, without her help, Arnold would not have been able to do his work. So Martha Williamson was a Victorian naturalist. She was based in San Pedro. She hung out with a group of scientists down in what is now Terminal Island. And she made extensive fossil collections around San Pedro, around Redondo Beach, even as far inland as Compton, places that are actually now all completely built over. And so Ralph Arnold was able to access her collections, which are now at our museum. In fact, the founding components of our invertebrate paleontology and malacology collections are from Martha Williamson. All right. Perhaps the most notable feature of Ralph Arnold's work was his documentation of Dead Man Island. And this was unfortunately destroyed by port development in 1929 through 1930, completely taken away. It was the most complete succession of rocks in the San Pedro area. And it was a regular stopover at that point for geologists and paleontologists. There were rich pickings, and you could learn a lot about the change in faunas that were living in Southern California, just in this one little succession. So there was a lot of interest in it. It was at the southernmost tip of what is now Terminal Island, and most of Dead Man Island got reconstituted into the modern port of Los Angeles. It got its name from rather hastily buried soldiers that were killed during the Battle of Dominguez Rancho, which was, I think, in 1846 during the Mexican-American War. So, true story, there were skeletons on Dead Man Island. All right. So, moving on to the 1930s, and the Palos Verdes Peninsula was starting to open up. There are two more characters that I want to introduce to you. Ulysses S. Grant IV, he's the great-grandson of the US president and Civil War general. He was also our first invertebrate paleontology curator at the Natural History Museum before he left to become a professor at UCLA. And then this gentleman, Wendell Woodring, who was a paleontologist at the US Geological Survey. And before I even ended up in Los Angeles, I was following these two gentlemen around the world in their adventures. I kept stumbling across their former field sites, so I know them quite intimately. So they made some significant contributions to our understanding of the geology of this area. And of course, their mode of getting around, unlike William Gabb, who had his horse, was the motor car. So that really opened things up. And I usually give this talk to kids. I like to have them appreciate just how hard it is to do work back then, the kind of work that we take for granted today. So initially restricted to just around the port, and then around coastal areas, and then on horseback, and now we can actually drive around good chunks of the peninsula. Not all of it, though, to map the geology. And Palos Verdes looked much different then than it does today. So it's largely ranching land, so road access to relatively undeveloped parts of the peninsula. And of course today, a lot of that is covered in buildings and golf courses, and also landslides. Landslides that have happened in historic times, which have obliterated, some of the underlying geology. All right, the emphasis on geologically mapping the peninsula was really spurred on by oil men. So exploration of petroleum was taking off in the 1920s and 1930s, and the oil men really needed to understand the geology in the basin, where the oil was coming from. Back in those days, very hard to see what's going on underneath you. So they would go to parts of the geology around these oil-producing basins that have been uplifted and exposed and available for study. And the Palos Verdes Hills are a particularly good example of that. It's the same geology in the Palos Verdes Hills that we have under the basin of Los Angeles, just much more accessible. So that was the motivation for understanding the geology of the area. And this is the first geological map of the peninsula, but it was an impressive product. And when you consider the work that was taken not only to map the geological units, these different colors, but also to do the survey work that underpins this, all the topographical mapping. So this map took about 20 years to produce. It's quite an effort, all right? And about 50 years later, we have our latest version of that map. Not a lot has actually changed geologically. It's different colors, they're a little bit brighter, but pretty much the same units that we recognize. The big differences are really in the detail. So if you look at this particular inset, there's lots of arrows and lines that indicate the tilting of the rocks and the folding of those units, and also the distribution of both historic and ancient landslides, which, again, as you see in this inset, are all over the peninsula. So geology is quite important to a lot of what we do in this area, in terms of construction and roads and the like. I'm sure many of you are familiar about that as you're driving around the peninsula and you're hitting those bumps and actively moving landslides. Okay, so I expected to have a few kids in the audience. So I tried to liven this talk up a little bit with this time machine right here. We don't really have time to talk about the nuances of the geological time scale, but I was going to use Cabrillo Aquarium's new time machine to take you guys back in time and have a look at what Palos Verdes looked like in deep time. All right, so if we go back 1 billion years, let's see what happens. Nothing so far. Invalid entry. All right, and the reason for that is there is nothing that remains of, well, I don't know how to describe it really, but there are no rocks of that age in the Palos Verdes area. And in fact, the closest we can go, basically Palos Verdes, the area that is now here did not exist at that time, so you couldn't go back in time there. Luckily, the time machine didn't send us somewhere else. But anyway, the closest we have 1 billion years ago is out in Death Valley. At that time, some of the continents are close together. I think California is in this narrow little sea ray right here. The continents are starting to split apart at that time. And there is a shallow sea in what is now eastern California and Nevada. All right? And in that shallow sea are growing stromatolites. So we see them today in places like Western Australia, these mounds of algae and bacteria that are cemented together by mud and sand, and they form these very characteristic stripy rocks. So we have a shallow sea in eastern California and Nevada. That's the closest we can get to 1 billion years ago. Let's halve that and see what happens. Oh dear. Still nothing to see. Palos Verdes doesn't yet exist as an entity. But we can go out to the Marble Mountains in the Mojave Desert, and we can see Cambrian age rocks out there. Cambrian is the name of the period 500 million years ago. Now, a lot has changed. We are in the southern hemisphere, just off the coast of this continent. Here we are over here. If we zoom in, you can see the California, Nevada, here's Nevada right here. So California and Nevada are a big shallow platform, and there would have been trilobites swimming around. This is one that we find actually in the Mojave Mountains and also further north in the Inyo Mountains, Olenelis. But still, we don't have any record of Palos Verdes of that age. All right, let's try again. 150 million years ago. All right, we got something. We got a hit. And of course, many of you will think of the Jurassic, and we have dinosaurs in the Jurassic. Not so much in California. In fact, I don't think we have any Jurassic dinosaurs in California. And the reason for that is we're now off the coast. The rocks that make up the core of the Palos Verdes Peninsula are way out to sea. They're in the subduction zone, which is a bad place to be a dinosaur, let alone any fossil. And in fact, all of the rocks we have of this age have been metamorphosed. They've been scraped up off the seafloor, cooked and pressured, and occasionally you can see fragments of fossils, but it's pretty bleak, really. But, we're on the scoreboard now. We exist. And basically, where we are then is a subduction zone. We have an ocean plate going under this continental plate, and the sediments that we have preserved in the middle of the Palos Verdes Peninsula, which are also found out in the outer Channel Islands, are these ones being subducted here and scraped up. And an example of this is the Catalina schist. So if you go hiking up George F. Canyon, you'll see outcrops of the Catalina schist, also exposed on Catalina Island. All right, let's keep going through time. Our trusty time machine. Oh no. So Cretaceous, actually, that was a misfire because no, you're right. I'm getting all confused here. We don't actually have a record of the Cretaceous in Palos Verdes Hills, but we can go inland to the Santa Monica Mountains and the Simi Hills and the Santa Ana Mountains and see Cretaceous age rocks. At that time, we were again a shallow sea and just off from the mainland. There are dinosaurs running around the hinterland of California. You can find them up in the Central Valley. There's also dinosaur bones found in the Santa Ana Mountains, isolated bones that have been washed out to sea, but no dinosaurs in Los Angeles County. All right, so no record of the Cretaceous out here in Palos Verdes, but exciting things are happening. And probably swimming around the waters at that time would have been this beautiful ammonite called Eupachydiskis. This is a specimen from the Santa Monica Mountains. It weighs about 150 pounds. And we're currently reconstructing that. It's on, the actual specimen is on exhibit in the museum in our new exhibition. But we're reconstructing this. We're going to bring it back to life, and including all the soft-bodied parts. And hopefully that's something that you'll be able to see at the museum very soon. All right. We're getting a little bit closer towards the present time, and this is where we have a continuous record. Really, geological time on the bottom, 40-odd million years to present. This is kind of a silly chart that I put together that really describes what is happening geologically, and it's intense. California is, for most of the last 150 million years, has been on a plate boundary. And that means bad stuff is happening. It's an active plate boundary. Rocks are colliding. Rocks are being subducted and buried and melted. They're being pushed up. You've got volcanic eruptions going on. And so there's a lot of deformation going on. You've got basins that get pulled down, subsided. Then you get mountains that are being pushed up and squeezed, compressed. And then you get some stretching going on as well. We'll get into that in a little bit. You've got the Gulf of California that's opening up like a zipper. The activation of the San Andreas and San Gabriel faults, things that are prominent features of today's landscape. All right, so 20 million years ago, this is just quite a dramatic event. The Santa Monica Mountains, the Santa Ynez Mountains, what we call the Western Transverse Ranges, and all of the rocks to the south and to the north of them have been rotated and have moved 200 miles to the north. 200 miles to the north and rotated over 90 degrees. It's quite a dramatic tectonic event. Starts about 20 million years ago, finishes about 15 million years ago. So where we're standing right now, that has gone on that ride for about 5 million years, quite chaotic, rotated north. And originally, the rocks that we stand on today and the rocks in the mountains were part of the North American plate. Today, they're part of the Pacific plate. So the Pacific plate, as it's riding north, so San Andreas Fault, you've got the North American plate going south, there's Pacific plate going north, so sliding past each other. The Pacific plate comes in and it grabs a bit of the North American plate, rips it off, spins it around, and that's us. So it's a very dramatic event. Oh, that's interesting. But quite critical for a number of reasons that I'll get to soon. Now I'm going to tempt fate and see if I can, play a video. Yeah, you know what? I'm not going to be able to play the video. That's very sad. But if you go on YouTube, Plate Tectonics, California, you'll probably get this. A really neat animation by Tanya Atwater that shows what happened. And Los Angeles, Santa Barbara, you would see that 20 million years ago, they were down by San Diego, further to the south of the Mexican border. And so they've moved north and they've rotated around as these plates have been gliding past each other. And it's quite a dramatic event geologically. All right, so how do we know this? You can look at the colors of the geological map, and you can kind of match them up with the rocks that are down in Orange County in San Diego. One of the notable things about the Santa Monica Mountains and the Santa Ynez Mountains is that they're running east-west. There's only 6 mountain ranges in North America that run east-west. All the others run north-south. So what these geologists have been able to do is if you just spin these back around, you can match up the colors, the different ages of rocks, J for Jurassic, K for Cretaceous, P for Paleocene. You can match them back up, and so there's some evidence that maybe these two were associated, and you can kind of draw a curve to suggest that they've moved in that direction. More empirical evidence is to look at what's called paleomagnetic orientations. So when sediments are laid down, the magnetic minerals in them will orient towards the poles. Okay, so they would normally be oriented to the north. And what we find with the rocks in the Santa Monica Mountains and also offshore here is that they're all oriented towards the west. So again, suggesting that they've undergone this more than 90-degree rotation. All right. So that was pretty cool. And what's neat about that is it creates what we call a basin. It creates the Los Angeles Basin. And this is the start of the fun as far as I'm concerned, because you can't have a fossil record if you don't have a sedimentary record, right? So we failed on finding the Precambrian 1 billion years ago, and we failed on finding the Cambrian. That's because we didn't have a place to put and keep all those sediments. So as that chunk of the plate is rotating around, it opens up a big basin. And basin, in a geological term, is just like a basin in your kitchen, or your bathtub, or a salad bowl. It's a vessel in which you can put stuff. And geologically, we're going to put water in it and anything that the water carries, like sediment. All right, but that sediment's got to come from somewhere. So just like if you're cooking at home with your basin, you need the ingredients. The ingredients are the sediment. And fortunately, we have some mountains being uplifted in the background, providing a regular source of sediment, sand and mud and gravel. You need to get it out to your basin, so it's where rivers come in. And of course, we have done some horrible things to our rivers in California, but maybe we're starting to undo those. And just to bring it back to marine biology, that has an impact on our biota living in the oceans today, right? All right, and lastly, you need a place to put it, and that's the basin or the sink, which is in this case the Pacific Ocean. All right. So this basin was rifting apart. In order to keep making a sedimentary record, you need to keep deepening your basin, because it's going to keep filling with sediment, right? So you got to subside your basin, and that was happening because it was rifting apart and sinking in the middle. All right, and we can see that. Here's a little model of that happening. It's pulling apart in two directions. It's thin in the middle, and that causes it to subside. And if we use a technique that they use in the petroleum industry to find oil, seismic interpretation, it's where you send seismic waves down into the Earth's subsurface. Those waves reflect off characteristic surfaces. You can kind of map out what's happening in the subsurface. And you see this shallow on the margins of the basin and kind of deep in the middle. The deep part in the middle is actually what's directly under downtown Los Angeles. We have a record that goes, I think, down 15 to 20,000 feet of sediment just in the last 15 million years. That is a tremendous amount of sedimentary thickness. And that'll be important later on. All right. Coincidentally, at this time, California is becoming less tropical. It's moving to the north. But also the currents, the cold water currents, are becoming stronger. And they're bringing a lot of nutrients down into these basins. When you've got nutrients, you can support a rich flora of algae, diatoms in this particular instance. They fall to the seafloor, they die, they're made of silica, they fall to the seafloor, die, and they form what we call diatomite, which in many cases was being mined commercially around the Palos Verdes Peninsula. So very productive environments, and that supported a tremendous food web. So all sorts of organisms eating those diatoms, and of course, other organisms eating those organisms. So I'm going to work through some of those. A lot of marine mammals, a tremendous fossil record just found in the Palos Verdes Peninsula in these cliffs. Just below, here's Point Fermin, but all along the coastline, a lot of fossils have been found. So this is Pontolus magnus. It's a walrus. And it doesn't look like a walrus, so it doesn't have the big tusks. And that's because walruses back in the Miocene, 15 million years ago, were predominantly fish eaters. Whereas today they're eating clams and crustaceans and anything that they can dig up in the sediment. They were also living in California at that time, which they don't today. They're restricted further north. So we've got walrus. Here's a fossil of a leatherback turtle. There's a skull of it right there. It's actually quite nicely preserved. So the leatherback turtle swimming around. And this is another really cool fossil that's found on the peninsula. It's called Corson's strange seal. So another one of these discovery stories. Mr. and Mrs. Corson were out gardening one day and dug this up. I think this was in the 1950s. And I'm sure they got quite a surprise. But this was in their garden. And it's a kind of seal. It's a little bit different, hence it's called a strange seal. It's a nearly complete specimen. That is on exhibit at the Natural History Museum. And I failed you all. I didn't get any nice pictures of the whales that have been found around the Palos Verdes Peninsula. But many of you as members of the Cabrillo Aquarium will be familiar with the one that's just down by Point Fermin. And you can find them at many other locations around the peninsula, such as Bluff Cove. There are specimens in the big boulders that are being pushed around on the foreshore there. Here is our marine mammal curator, Dr. Velez Arabi, explaining what it is that is significant about the whale that's down at Point Fermin. All right, so that's good. But the diatoms are important for another reason. The organic material that is contained in them when they fall to the seafloor is the building blocks of petroleum. Okay, and we had a massive explosion in the exploitation of that resource in the 1890s and the early 1900s around Los Angeles. Of course, it was being exploited long before Europeans arrived on the west coast of North America. It was important to the indigenous people. But we came along and started putting up all these oil derricks all over the city. And even the world's first offshore drilling was this is in Ventura County. Doesn't look offshore by today's standards, but this was the technology at the time. You build a pier out into the sea and you stick a derrick on the end of it and get access to so much more oil. And I'm sure many of you are familiar with walking on the beaches in Ventura and Santa Barbara County and stepping on tar. There is a lot of oil both coming out of the hillside but also washing up on the beach, a lot of that from natural seeps. So that is what the petroleum geologists were after at the time. And then I love this photo. This is Huntington Beach in the 1920s and Huntington Beach today. And you can't really tell the difference. There's people flocking down to the beach and sunbathing and they got their umbrellas and having a good old time, just like they are today. But look what's in the background. It just blows my mind. Just this tremendous industry of petroleum exploitation taking place. It all comes from the diatoms. Signal Hill in 1924, I believe. Peak oil production was in 1923. So it happened very, very quickly, just in a few years. Probably no regulations at the time. No expert on these things, but I imagine that's the case. You see how close all of these derricks are together, and they're just pumping that oil out. And it's oil derricks everywhere. All right. Now, the oil is not found all over the city. It's found in particular spots, lineaments, and these are aligned with major faults and folds through the city. Okay, so the the oil fields are concentrated where they are, these faults and folds. So an understanding of the geology is really important for finding the oil. And it turns out, here's a couple of these major fault zones. The Newport-Inglewood fault zone, which many of you might be familiar with. I mean, it's one that can generate earthquakes. The Whittier Fault, and also the Palos Verdes fault zone. Now, the Palos Verdes fault zone, before I forget, is what has uplifted this peninsula. So we went from a phase of rifting and pulling apart, what we call extension in geological terms, to compression. It's now all being pushed back together again, and these faults are actually below the surface, so we call them blind thrust faults, and they're being pushed together, and that is what is pushing up the Palos Verdes Hills. It's what pushes up the Baldwin Hills, the Inglewood Hills, the Dominguez Hills, Signal Hill, these faults. And now that's important for the oil industry because the oil tends to transport up through these faults, but also be trapped in these domed sediments. And we call these oil reservoirs. So the source rock is down here. It's that diatomaceous sediment, and it's rising up through the surface, and it gets trapped under certain impermeable beds. All right. And even today, the oil industry might have slowed down a little bit, but there are oil wells throughout the city. We do a much better job of disguising them. But more than 500,000 people live within a quarter of a mile of an active oil well. So it's something that's really important in terms of environmental and health concerns. All right, whoa, it's going to be a little bit hard to read, but we're now arriving closer to the present time. And what I want to introduce to you is the last couple million years. Sea level is fluctuating up and down, and it does it at quite a regular beat. Regular climate change. This is associated with growth and expansion and then retraction, shrinkage of the continental ice sheets. All right? So the Earth has a bit of a change in orbit around the sun every 100,000 years or so. It's also got a bit of a wobble to its tilt at shorter time spans. And all of those factors can work together to mean that the poles can get more or less solar insolation, solar energy through geological time. And that causes these ice sheets to melt and then to grow again. When they melt, of course, all that water is in the oceans, causes sea level to go up. And when they grow again, that water is trapped on land, causing sea level to drop. And sea level has been going up and down. Let's see if I got another picture of it. Yeah, there we go. Every 100,000 years by about 100 meters. So it's quite dramatic. All right? And of course, that is all recorded on our landscape. So let's see what we got here. Here's some evidence for some of those ups and downs. If you look around the city of Los Angeles, there's Pleistocene, late Pleistocene fossil records all over the place. These are commonly within this line, or at least around the edge of what we presume was the shoreline at that time. So there's a fossil record telling us that these environments were underwater. And we also have on the landscape these terraces, these parts of what would have been underwater coastal wave cut platforms that were being eroded by the sea, and then ultimately uplifted and stranded on land so that they're preserved for geologists to come and look at and for people to build on. We also have other evidence of marine environments like boulders with boreholes in them. I'm sure if you've walked on the beaches around the Palos Verdes Hill coastline, you've seen many boulders with boreholes in them. You can also drive around the upper parts of the hills around PV, San Pedro Hill, and see boulders with boreholes in them. And that is evidence of some of these older sea level rises. We also have uplifted sediment. Remember I said there's these fault zones where sediment is being pushed up. So for example, Baldwin Hills, a great place to go hike. You're walking up Pleistocene sediments with fossils in them. All right. Then if you look at a topographic map or a bathymetric map of the bay, the Santa Monica Bay, you can also see this large flat area of the shelf. And that is a record of when sea level dropped to its lowest point, which is about 12,000 years ago. So sea level went from being inland and encompassing most of what we call the city of Los Angeles to being further offshore. So, if you had beachfront property in Redondo Beach, you've now got quite a walk out to the beach about 12,000 years ago. All right, and of course we have the modern day coastline. So this is all evidence of coastlines retreating and expanding through time, and that's happened over and over and over again. We have a deep record of that. I just want to show you a quick, no, it's not going to work either, is it? Because I broke my presentation. But I have an animation that shows what happened to the Los Angeles Basin over the last 100,000 years as the shoreline moved across it. And I want to point out that La Brea tar pits for most of that time was underwater. So only in the last 50 or 60,000 years has that particular place, which is such a rich fossil record of terrestrial life in Los Angeles, been above sea level. Okay, here's some more evidence of these terraces before things got built on them, and you see one right here. You also see the modern day wave cut platform down here. So this one stranded up here at the top of the cliff was a beach about 100,000 years ago. And then there's another one there and another one here and maybe some more up there. Over time, the evidence of these gets weathered and rounded and less obvious for us. But that's where all those boulders come in. They stick around, and you can find those when you're out driving and hiking and riding your bikes. And again, these were fantastic places to build houses on. Nice and flat and none of those hilly roads. Where we live, the Palos Verdes Hills, was in fact an island for most of the last million years or so. So the city of Los Angeles was further to the north. Here's Redondo Beach, here's Torrance, they were in the water. Lomita was beachfront property. Very nice, shallow, warm embayment right there. Wilmington was shallow water. And San Pedro was right on the shore. And this would have been an island. And as a result, we have a rich fossil record all over the peninsula, particularly in San Pedro itself. So these are buckets and buckets of shells collected from downtown San Pedro. Here is another fairly recent construction site on 5th. Happened to be driving by one day and I saw this big pile of dirt, and that got me very excited. It was actually the day that I was heading out of town on vacation with my family, and so that actually got delayed. I got in a bit of trouble for that. But you can see why. I mean, you would have stopped too. Look how fossiliferous this is. And again, these are these fossils, about 125,000 years old. And even the construction workers were getting into it. I often find this. I get a lot of help from the construction workers because they want to know what they're digging up. And again, downtown San Pedro, this amazing archive of past environments. All right, so I want to leave you with this message to as you're driving around Palos Verdes, as you're driving around the city or around the state, to look out the window and try and block out the buildings and the roads and see the mountains and the coastline and think about how they got there. There's often a geological story to it. And so my reminder to my colleagues that, these guys are cute and adorable, but they don't represent the complete history of Los Angeles' fossil record. It's more like this. I like to flood the city and have lots of marine critters swimming around. This is what the bulk of our fossil record represents. Okay, and lastly, come to the museum and see the exhibit, learn about these discovery stories. You can look at an interactive map and find out what has been collected in your neighborhood. The kids are loving it. There's lots of reconstructions of some of these ancient creatures. This is a desmostylian, a kelp-eating marine mammal, which we don't have any of those in Western North America anymore. Yeah, kids are fixated. Here's this interactive map. So here's San Pedro, and these are some of the Point Fermin elementary school kids checking out all the dots in their neighborhood. And of course there's Megalodon, and who doesn't love Megalodon? All right, so thank you very much. I'm happy to take questions.
Great. Let me just get a check from home that they can hear me as well.
Oh gosh, I hope I don't have to repeat all of that.
No, just that they can hear me because I'm going to repeat the questions. So if you guys have any questions for Dr. Hendy, I'm going to repeat your guys' questions so the folks at home can hear them as well. But you could go ahead and
All right.
choose whoever you like.
Oh, we have a hand way down the back there.
What do the boreholes have to do with land rising and falling?
Okay.
What
Yeah.
do the boreholes have to do with rising and falling?
Yeah.
Sea level change.
Yep. Yeah, I didn't fully explain that, did I? If you walk around the beaches around PV, you'll see these boulders with boreholes in them, and they're made by a limited number of animals. There's a couple different kinds of clams that create them. Two distinct families, they're called pholads and lithophagids. They are primarily restricted to the intertidal and shallow subtidal. So if you find a rock with those very distinctive boreholes in them, they're kind of a torpedo-shaped or teardrop-shaped, you know that rock has been in an intertidal setting at some point. So if you're finding them at 1,200 feet above sea level at the top of San Pedro Hill, you know that at one point, unless someone put it in their garden, and this is something, you may find me snooping around people's gardens in PV in the weekends. I do this. So I've always got to find more than one boulder to be sure that it's not a landscaping trick. But you know that place was at one point in the intertidal, and it's since been uplifted. Yeah, another question down the back.
The ancient sea over eastern California and Nevada, was that freshwater or saltwater?
The ancient sea over, say it again, the ancient sea, what did you ask? I'm going to repeat.
Eastern California and Nevada.
Over eastern California and Nevada. Was it freshwater
Yep.
or marine?
Yeah, that was marine. That was marine. And possibly at some points it was hypersaline. So these stromatolites are capable of living in quite extreme environments. So they can live in high salinity settings. So you can imagine these very, very shallow seas with not much circulation, might have a lot of evaporation and could be extra salty. But I don't know of any freshwater rocks of that age. Now, stromatolites, these algal mounds, can live in freshwater. They can also live in salty water like Great Salt Lake. There are algal mounds there. Yeah. Okay, up the front.
Thank you for the interesting, informative presentation. My question is, how old is the Earth?
How old is the Earth? Okay. Yeah, I didn't set the time machine to go back that far, but we're talking over 4.6 billion years. Yeah, and we have, we've got rocks a little bit younger than that in parts of North America, but I think the oldest are in places where there's been a lot less tectonic activity, like Australia and maybe in Africa. But North America has gone through a lot, so you have to go up to sort of Minnesota, Wisconsin, Ontario to find rocks of that age. But I think the oldest in California is a tad over 1 billion. Yeah.
Thank you.
Yeah. Oh, we've got a couple down on the right-hand side there. We'll do the one towards the front.
I lived in Las Vegas years ago, and I used to go up to a site in Sunrise Mountain that had trilobites in green shale. Does that mean it was in seawater?
Something
Yeah.
about trilobites in Las Vegas. Are they marine or are they from
Yes,
shale?
they were in a green shale, and yes, they would have been marine. I don't know what is causing the color patterns, but we have those in our collection. They are very green. Sometimes they can be very red. One of the fascinating things about a lot of the trilobites in those shales, again, I keep harping on this, we're in a very tectonically active area. You'll often see the effect of those tectonics on the individual trilobite fossils. They will be sheared, squeezed, and very asymmetric as a result of the rocks being compressed and twisted. It's quite fascinating.
Salt water?
Yeah.
Asking if shale is salt water. He said yes.
All right, there was a question further back there.
So we,
Oh, hey, Diane.
we very much enjoyed you on the Baja adventure this year, where you brought lots of excitement and enthusiasm.
Diane's talking about how
So
Dr.
much
Hendy
trip.
was on the Baja trip this year.
I wonder if you might share real briefly your San Benitos experience.
Oh my goodness.
And she's asking about him to talk about his San
The special
Benito experience on one of the islands on our Baja trip.
Okay, that was with the rookery.
I'm being too vague. You discovered a
Yeah, okay, absolutely. So I don't know how this really came about. It was such a blur, but Diane invited me to join the whale watchers heading down to Baja earlier this year, and we stopped at a number of islands off the Pacific coast of Baja, California, and one of those San Benitos, we did find, I'm trying to remember the age of the rocks, I think they were Cretaceous age rocks. These are deep sea shales. Most of them have been metamorphosed, like the rocks we see in the San Gabriel Mountains. I've been down in that subduction zone. They've been getting scraped up, caught up. The ones that survive are the ones that got caught up. And typically you don't expect to find fossils there, but I'm always looking, and nothing gives me more motivation than being told that there aren't any. And yeah, we did find some trace fossils, some worm borings. And there no doubt are more, so would love to go back next year and send out a search party and see if we can find more. But it's exciting to find the first record of something in a place where they're not expected. So yeah, there's discoveries to be made everywhere. I emphasized this at the start of my talk, that we can all make these discoveries. And yeah, you just got to keep looking. Yes?
A minute ago, you talked about the oldest rocks in Southern California. The oldest that I'm aware of is the Mendenhall gneiss, 1.2 billion years old.
Okay.
1.2 billion year old rock.
Yeah.
It's usually thought of as something that happened under a continental collision.
Okay.
So before the rifting, you were talking about 1 billion years ago.
Yeah.
They had to come together.
Yeah. And I showed you
He's
what's
asking about rifting.
called a paleogeographic reconstruction, and you see continents that are moving apart. There's shallow seas, and if they're moving apart somewhere, that means they're colliding somewhere else. So this is happening throughout geological history, and these gneisses are metamorphosed rocks. They have been pressurized and heated and had some alteration. And yeah, I'm very biased towards the fossil records, so I steer clear of reading those papers and focus on the ones with the fossil records. So we start seeing these stromatolitic horizons, I think just more than 1 billion years ago, and the first evidence of primitive life in California. And then 500 million years ago, that's when we start seeing more complex life forms, the earliest arthropods, and the earliest mollusks and corals and sponges and things. Yeah. All right.
Can you talk a little bit about some of the fossils you found in the construction site? It looked really cool.
She's asking about some of the fossils that he found at the construction site.
Well, there's a lot of them. We have hundreds of sites across, and you know, this is something I've just done recently. Is we didn't know how many construction sites were represented in our collection. We had to work hard to figure out that number. So it's in the hundreds of localities around the city. I think the most interesting to me are from the subway excavations, particularly the Red Line, which was in the 1980s, that was being dug close to downtown. Just tremendously rich beds of clams and snails, crabs, things like that. And no one has ever really studied those adequately. It's on my quite lengthy to-do list. But we have extensive collections that are a result of that, what we call mitigation work. And California is one of the few places where that happens. So it's as a result of the California Environmental Quality Act that was, I think, passed in the 1970s, called SECA. And that mandates that, you guys know about this?
Yeah, I'm an environmental.
Oh, okay. Well, I'll face over here to the other audience. But yeah, it's critically important for us, and well, for you, in terms of preserving that natural heritage around the city, and also archaeological records. Most states do not have such legislation. But one of the interesting things about it is it's enforced at a local level. So counties and cities have jurisdiction over their local areas, not at the state level. And therefore, it's enforced very unequally. So I would say there's a lot more destruction of fossils and archaeological remains going on than there is conservation, because it's easy to forego these regulations if no one is policing them adequately. So if you go across the border into Orange County, it's a little bit harder to get away with digging a hole and not saving the fossils you find there. It's quite fascinating. All right.
Let's take a question from home.
Okay.
Okay. What is significant about the whale at Point Fermin?
Oh gosh, I should have studied up on this, Diane. What is significant about it? Well, what is interesting to me, I mean, it's a well-known whale. No doubt many of you have been taking field trips to there for decades. So it's quite eroded. It's well-loved and somewhat eroded by coastal erosion. But what's interesting about it is a lot of it is preserved. Bit beat up, but it's preserved. So you've got the back of the skull, and you've got part of the mandible. In fact, you can look into, it sounds gory, but it's not. You can look into its brain case. It's been eroded out by the waves. So you can actually see inside its head. Not much going on there today. And then it's the upper trunk. You got little sections of the backbone that have been disarticulated. So this is interesting. What you will often see with whales, but this is also true of land animals becoming fossils, is the head will often break off from the rest of the body. The backbone sticks together, but the skull is usually very heavy, right? And if it's in a river or stream, or even tossing around in waves and currents in the marine environment, the skull will break off eventually when the muscles break down and roll away. In this case, the skull is there, part of it, and then there's little sections of backbone. They're not all attached, they're kind of oriented in different directions. So they disarticulated on the seafloor, but didn't go too far. And there's also a few ribs, maybe part of a flipper. And I'm not a whale person, so I think I've done pretty good remembering all the parts so far. But the reason it's relatively complete is it's in a deep, deep marine environment. And nothing much happens there until something happens. And so I know that sounds kind of silly, but in a deep, deep setting, there's very little sediment being accumulated. Nothing's happening on the seafloor. But periodically, there'll be an earthquake or a storm, and a lot of sediment will be washed down from the shelf, and it can be quite chaotic, and it could completely obliterate one of these whale falls. In this particular case, it seems that the whale got buried before it got kind of completely disarticulated and disassociated. So it's kind of cool. I think, if I remember rightly, Diane, maybe you can remind me, it's maybe in a group that's related to the pygmy right whales, cetaphers. It's a cetaphar. Oh, the whale people are
They're not sure.
looking around each other.
They're not sure,
I
yeah.
thought it was a relative of the gray whale. I thought that
Gray whale?
Yeah.
All right.
They're not sure, yeah.
Jorge would know better, I'm sure.
Yep. So it's in my phone, but I dare not go looking for that piece of information. Yes?
The fossils you said were on Fifth Street, is that due to the courthouse demolition?
Oh, I don't know where the courthouse is.
Oh,
but
she's
it's
asking about the fossil excavation or the
Fifth and
construction on Fifth Street.
Pacific. Pretty close to Pacific. Yeah.
If it's near the courthouse.
Yeah.
Fifth and Pacific?
And the site is now built over. The building's gone in. And I would say at the moment, over the last few months, there's been 2 or 3 other sites in San Pedro. And typically what happens is we get a call or an email from the mitigation paleontologists when they've finished the job. And they're like, here you go, here's a bucket of stuff, which is very disappointing. I mean, it's exciting, but it's disappointing because I always want to see it in context. But I've had no emails or phone calls about these sites. So, you know, I think there's a lot of salvage work that's not being done. But, you know, someone's got to go around and chase these people down. I can't do it.
What should be done if you're digging in your backyard and you find something?
What should be done?
To remodel your yard?
What should you do if you're digging in your backyard and you
Oh, you
find
call me.
something?
And no,
You call.
seriously, I've really taken it upon myself to answer all of the emails and phone calls from people who find stuff, and it is a real blast. I showed you those kids at the very start, Avery and Aaron. I went out hiking with them this past weekend. They took me to their site where they found the fossils. You know, it's a teaching moment. Hopefully you're curious about what you dig up in your backyard. And I just love to share that knowledge. But, you know, it's likely to be significant. So, it belongs in a museum unless you get pleasure from having it in your house. So, but it's good to know what it is. Yeah, so call your local museum.
Any other questions?
All right, well, thank you, everyone. This was a blast. And, yeah.